Okay, we're given a charge and a capacitance. I'm sorry, we're given a capacitance and resistance, right? So we want to know what the charge is as a function of time if we're discharging through the resistor. So we have this circuit. Okay. Now I didn't give you an initial charge, so you're going to have to assume a charge Q. Okay? So assume charge Q. You have your resistance, you have your capacitance. Now you know your voltage at this instant, right? Voltage is Q over C. Okay? So the current equals voltage over resistance equals Q over RC. Right? Well, what's current? Current is dq dt okay? Now, the only thing I've got to be careful of is a sign here. Okay? So your basic idea is, as you go around the circuit, your voltage from any point on the circuit back to that point, you're changing your potential difference between any point on the circuit and itself, if you go around the circuit, has to be what?
Same. Like, they all move.
Yeah, okay,
As a cloud.
the voltage has to be the same, so the change in the voltage is, the potential is the same here as it is here. Now, because the field's conservative, okay? So whatever's going on with the field through this whole circuit, the work you do on a charge to get from here around to here has got to be zero, okay? Because of the conservative field. So that's the basic principle, right? So the change in voltage, or the change in potential as you go around here is zero, right? Okay? Well, if the voltage goes up as you go across the capacitor, then your conventional current is in this direction, right? What happens to the voltage as you go across the resistor? Well, if you measure it with whatever instrument, the voltage drops. Okay, so voltage goes up, voltage goes down, and now it's back to where it was, right? Okay, so whatever the sign of your capacitor charge is in the direction you choose, the sign of your voltage change is going to be opposite. So that when I write this, I should say this is negative so that this is negative. Okay? And this should be negative. Again, because if the voltage goes up as you go across here, it goes down as you go across here, and you got to choose a direction for your loop. So we choose the direction to be whatever the direction of conventional current would be. So if the positive is over here, well, we're going to go this way. Yeah, you can use other conventions. Either way, you get this. Okay, does that make sense? You've seen this equation. It's been asserted. You've used it in differential equations. You know how easy it is to solve. Okay? So we're not going to go through the details of that. You get this, where Q naught stands for Q when t equals 0. Okay? And then, of course, your current equals I naught e to the negative t over RC. And this is because your voltage is what? Q over C, right? So you conclude that your voltage equals V naught e to the negative t over RC. So once you get this, your voltage being just a constant multiple, you have this, right? Okay? And your current being voltage divided by resistance is just another constant multiple of this that we might as well write this way. Now you want to think through all those details. Okay? So if you didn't understand all my statements, this would be a good video to take a look at and understand my profound wording. Okay? And if you can find another wording you like out on the internet, go ahead and find it. I won't be hurt at all. I just want you to understand it.